All right, so let's try in physics better, okay? All right, so this is actually an excellent question. I like this question a lot. I used to be able to do this as a demo, and I just need to make new pucks. My old pucks wore out because I now have an air track. My old air track broke, so I have a new well, it's not new. It's been in here for a while, but I have an air track. So we'll be able to do this. I just have to get the pucks fixed. I just have to put new Velcro on them. So all right, so imagine I have the two pucks and they are going right at each other like this. Okay. And we have mass and stuff here, but let's just, for the time being, M and V. Is that okay? Are you guys all okay with that? All right. Allie, you're going to help me out, okay?
Okay.
Pick a direction that we're going to call positive.
Is this like a left or right or up or down?
Okay, we can do both.
Let's just up's positive. Left is positive.
Okay. Now we're looking top down on the table. Does that make sense to all of you? So right now, the pucks are both traveling purely horizontally, and I put that red line in there as a point of reference. Does that make sense? The momentum of this system would be 0 because the left puck is traveling in the negative direction and the right puck is traveling in the positive direction. So they'd have a momentum of 0. But also, because they're traveling along this line, if they were to stick together, they'd stick together and stop. Does that make sense? But that's not what the pucks are doing. The pucks are traveling like this, right? One of them slightly higher than the other one. So this is more a picture of what the pucks are doing, correct? Now, this is still true. This has not changed at all. It's still true that the linear momentum is 0. But is it clear to you the pucks still have a good chance of coming together in the middle? So let's mark the spot where they come together. If we recall, one of the things we talked about when we talked about the kid running towards the merry-go-round was that if we draw a line from the middle of the merry-go-round to the kid's straight line velocity looks as though it's rotating around a point outside of the kid. Do you remember me doing that? If not, let me do it again. So I connect a line from the point where the two pucks are going to meet to the top puck. Now, if I'm paying attention to the blue dot, which is where the two pucks come in contact, the top puck, oops, lost my little line. The top puck is going to go this way, right? Doesn't that look like it's rotating around like that? You guys see that? That would suggest that if I wanted to use my blue dot as my point of reference, the top puck does have an angular momentum relative to the blue dot, and it would be in the clockwise direction. You follow what I'm saying? So let me do that again. I'm trying. Right, it'd be in the clockwise direction. Isn't that clockwise? Now, if I start my line at the other puck, which is below the line, and I do the same thing, as this puck goes this direction, isn't it true that it's also having kind of sweeping out a rotational vector that is also clockwise? Well, what that means is that although their linear momentum is opposite, their angular momentum is complementary. They both have an angular momentum in the same direction, in a rotational direction that is clockwise. Go ahead.
But wouldn't the velocity still still be negative, or taking into account them a spin, you just forget about that?
Well, I can show you technically why it wouldn't be, but I can also show you physically why it wouldn't be. This is me trying to show you physically why it wouldn't be. But let's talk about maybe technically why it wouldn't be, okay? Now, this is going to be technical. Are you ready for a technical discussion?
I'm ready.
When we first talked about angular momentum for a point mass, I said it was r times p times the sine of an angle. Okay? What I didn't tell this class or any of the other AP1 classes that the truth is this is a vector and it's r cross p. Now, we've had cross products before, like torque. Torque was a vector and it was r cross f. And we used our right-hand rule to describe cross products like this. So, do you want me to go ahead and continue this problem? Okay. So, I would like to be able to use the angular momentum as we talked about yesterday, where the angular momentum is r perpendicular times p. Is that okay with you guys? I think you'd prefer it too. So I'm going to advance the puck to the point where it touches the other puck. So advance the whole thing to this point here, where this one still has a velocity like that, and this one has a velocity like that. This is that instantaneous moment just before they stick together. That okay? Well, it seems to me that r perpendicular would be that. What does that look like to you? I think it's the radius of the disk. And I think the other one's r perpendicular would look like that. Isn't that also the radius of the disk? So, I think we can write the angular momentum of one of the disks as r, the radius of the disk, times mv. Put the numbers in later. Now, I think there's two of them, right? Two disks. So this is the angular momentum of one of the disks. Isn't the angular momentum of the other disk going to be exactly the same? So I'll have the angular momentum of this disk plus the angular momentum of this disk. And that's going to equal the angular momentum of whatever the heck this thing is, this two-disk monstrosity that gets formed in the middle. Is it not kind of clear to you that we're going to get something where at the end of the day these things are spinning around each other? Does that make sense? That's what we're probably going to see. So I'm expecting we can figure out how fast they are spinning after they stick together and start going around. That good for you guys? All right, so who's followed this conversation up to this point? Okay, we're doing okay then, right? So RMV plus RMV. They don't cancel out. They add together. Equals I omega. Okay, so we want the angular speed of the system after they come into contact. So we're looking for this right here. Now we are going to have to deal with the angular momentum of the system. And these are disks. They tell us to use disks, but are they disks spun about their center? No, these are disks spun about their edge. What would I have to use for the moment of inertia then? Do we know one about their edge? We know one about their center, right? So we might have to convert it to something about their edge. Do you guys remember what we used for that? Go ahead.
Wasn't it the original moment of inertia, mx squared?
Kind of. We have the moment of inertia about the center. What is the moment of inertia about the center of mass of a disk? 1/f m r squared. We're going to have to use something that we talked about 2 weeks ago called the parallel axis theorem. This is where mx squared came from. Parallel axis theorem we talked about 2 weeks ago. It's how you shift something's moment of inertia. It's on your equation sheet, and it should be in your notes, but if it's not, put it in your notes now. The parallel axis theorem allows you to take and move the axis of rotation to any parallel axis you'd like. Parallel axis. So like my original one was this way. I can shift it over to the edge, and now it's a parallel axis. Does that make sense? Easy enough? Now, I would not be able to do this axis, because this is not a parallel axis. This is a perpendicular axis. So it allows for any parallel axis. Now, if you don't believe it, we can do this one. This is what? If I rotate it about here. 1/12 ml squared. If I shift it from here to here, how far have I shifted it? Half of the meter stick, right? So think of it, let's just do a little aside. You guys know what an aside is? It's when you have a side conversation. So in this side conversation, we're going to shift the moment of inertia from the center of a rod to the edge of the rod, just to remind us how the parallel axis theorem works. So I, center of mass, plus mx squared. So the moment of inertia at the middle is 1/12 ml squared. We're going to shift to a parallel axis that's at the edge, so we are shifting by a distance of L over 2, right, going from the middle to the edge. So this is 1/12 ml squared, but 2 squared is 4, so this will be 1/4 ml squared. Everybody follow why I got those or how I got that? We good so far? Anybody confused? I see confusion. Go ahead.
Why'd you put it in front of?
So they look the same? I could have written it as m times L squared over 4, but they look the same now. Also kind of prove they have the same kind of structure to them. Because I'm also going to do this. I'm going to add them together. It's like 2 ml squared plus 4 ml squared, right, which would give us 6. But this is 1/12 and 1/4. So I'm going to get a common denominator of 12. And that'll be 4/12 ml squared, right? No, 3/12. Mr. Shelton should do math better. 3/12 ml squared. And when I add those together, I get 4/12 ml squared, which, as you probably can guess, is 1/3 ml squared. That look familiar? That's how the parallel axis theorem works. That's what we talked about a couple weeks ago. So, for us, we're going to shift the axis of rotation from the center to the edge of the disk. So, starting with the center of a disk, 1/2 mr squared, by how far are we shifting the axis? If I want to go from the center of a disk to the edge of the disk, how far am I shifting it? Anybody else besides Nathan? What's that? Well, we're just using M's and R's and L's and that. What would it be here? I'm trying to make it hard. Isn't it 1 radius? Are we going from the center to the edge is just the radius, right? We sure we get that? A disk has a radius. If you're at the center and you want to move to the edge, you're moving how far?
Radius.
A radius, yeah. So this will just be mr squared. Can we add 1/2 mr squared to mr squared? What do we get? 3/2 mr squared. That's right, 3/2. 3/2 is also known as 1.5. Okay, how many disks are there? 2. So this is the moment of inertia of 1 disk, but there are 2 disks. So this has to equal 2 times 3/2 mr squared times omega. And by the way, this side is just 2 RMV. We doing okay so far? Alrighty. There's not much left to do here. I cancel out the 2's. I can cancel out the M. I didn't even cancel out one of the R's. That leaves V equals 3/2 R omega. I know that we were given numbers, but sometimes it's just easier to do the letters first. So now I'm going to solve this for omega. And that'll be 2v over 3r. So we know that v is 20 meters per second. Wow, those suckers are hauling. Don't do that on my air hockey table. And they have an 88 millimeter diameter. That's an 8 centimeter diameter. That's 0.08. So 3 times 0.08. What? What's that?
Use half that. So the radius.
Oh, it's diameter. Okay. Oh, wait. I said 80 millimeters. Yeah, that's still 8 centimeters. So you're right, 4. So 0.04. Okay, that's the answer. And it'd be in meters per second divided by meters. So this is going to give me radians per second. Woohoo! So 40 divided by 0.12. 40 divided by 0.12. I got 1.6. That can't be right. 40 divided by 0.12. There I go, 333. Okay. Radians per second. Anybody else get that? No? Yes? Am I the only one doing this? Are we allowed to leave it in radians per second? Doesn't say we have to convert it to anything, so I think we're okay. I mean, RPM might make more sense because it's spinning so fast, but we don't have to. What is the loss of kinetic energy due to the collision? That sounds like more work, but we can do it. How many things have kinetic energy before the collision? Yeah. And just one thing has kinetic energy after the collision? All right. Let's do that then. There's the kinetic energy before the collision, 1/2 mv squared times 2, right? 2 pucks. They both have the same mass and all that, so that'd be the kinetic energy before the collision. And the kinetic energy after the collision would be 1/2 I omega squared. So this is just going to be mv squared, or 0.2 grams times 0.2 kilograms times a speed of 20 squared. So that's 400 times 0.2. I get 80 joules. Everybody good? 1/2 times 2 times 3/2 mr squared times omega squared. Everybody see where I got all those numbers from? So 2 times 3/2 is 3, times 1/2 is 3/2. So this will be 3/2 times 0.2 times 0.04 squared times 333 squared. Whew, that's a lot of numbers. So here we go, 1.5 times 0.2 times 0.04 squared times 333 squared equals, I get 53 joules. I didn't do anything weird, did I? Look, you guys have to be able to do this on your own. So right now it is 322. Could you do this on your own? If not, tell yourself what we had to do this. Pick a part and start there, because I usually stop halfway through and I didn't. So pick a part. If you don't know what to do for the energy, well, you use 1/2 mv squared for the thing that was going in a straight line, 1/2 I omega squared for the things that were spinning, and you compared the two numbers. Tell yourself what you need to do here.